Hey everybody and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy where we are learning networks together. And on this video, on the next part of this series that is about EVPN-VXLAN or Ethernet Virtual Private Network, Virtual Extensible Local Area Network. As I always say, those are two acronyms in one. In this next part of this series, what we're actually going to go through is not the route type 5, the EVPN route type 5, but we're actually going to go into one of the more advanced features and areas subjects of EVPN, and that is the IRB, or the Integrated Routing and Bridging feature. Now this is certainly more advanced. If you've not seen part 1, part 2, part 3 or part 4 in this EVPN VXLAN series, I highly recommend you start there. You definitely need to know the basics, the benefits of EVPN, and ideally EVPN route types 1, 2, 3 and 4. And here's just one of the links just for you to watch. But you need to know the basics before going any further. And of course, if you've got a basic idea of what routing and bridging is, that's going to be of huge benefit. Now, as I said, this is more advanced. We're going to be touching on IRB. Again, that stands for Integrated Routing and Bridging. And this is a big subject in the EVPN world because, as we know, EVPN is a signaling protocol. It's something that is built on top of the overlay, and the overlay is built on top of the underlay. EVPN is basically advertising to different VXLAN tunnel endpoints, the VTEPs, what MAC addresses are connected to a particular VTEP and flooding it throughout the area. That's where the EVPN route types 2 come into it. But there are different ways in the EVPN world that you can do routing. There is a asymmetrical model, and then there's a symmetrical model. So on this video, on this part, we're going to go through what is the asymmetrical routing type, what is the symmetrical routing type, what are the benefits and the disadvantages to both of these models, and as it's called, we're also going to go through the packet life, the packet journey in terms of an IP packet. What are the different headers you will see and the VNI that you will see within an IP packet with UDP headers, etc., as it goes through the network from one VTEP to another VTEP to another VTEP based on that routing model. But before we even get there, we need to start off on the basics of this advanced topic, and that is, what is a MAC-VRF, or Virtual Routing and Forwarding Engine or routing table? What is the IP VRF? How do VTEPs forward traffic when it's inside a local area network? How do they forward traffic when it's going from one VLAN to another VLAN within the same local area network? It's not the same local area network, but of course you need a gateway. So we're going to touch on first, why do we need routing in the EVPN world? What are the use cases for it? What's MAC-VRF? What's the IP VRF? And then that's going to build very nicely into the packet journey and the asymmetrical versus symmetrical routing types when it comes to EVPN. Again, this is an advanced topic, so take your time with this. We're going to start off with the basics, build onto the more advanced parts slowly, but I highly recommend you have a coffee as well, or a cup of tea if you fancy that. I'm more of a tea man myself. But other than that, let's just get straight onto the theory and start off with, what is a MAC-VRF? What is an IP VRF? Why do we need routing in the EVPN world? Okay, so let's actually start off with what is the difference between bridging here and routing. Obviously, those are two functions within the term IRB, integrated routing and bridging. So let's say we've got a host here, and that's me or whoever it may be, and let's just call it user A. And just for simplicity, let's also say this is MAC address A for user A. Let's just keep it very simple. And the user here, user A, is connecting to a switch port. Whatever the switch vendor is, it doesn't matter at this point. This is obviously a juniper switch that I'm showing here, but it doesn't matter. This could be any vendor. And let's say, for example, that connected to the same switch, we've got another user here, and let's call it user B with MAC address B. Now let's also then say that user A with MAC address A is in VLAN 10, just for example. And let's also say that user B with MAC address B is also in VLAN 10. And MAC address A, user A wants to send traffic, whatever that traffic is, to user B. Now when the user A first connects to the switch, what they're initially going to do is send an ARP, aren't they? They're going to send an ARP request, address resolution protocol, up to the switch, and the switch then learns what is the MAC address of user A, and it will store that MAC address in its MAC address table, or switching table as it's commonly called. And also within this address resolution protocol, we will also learn what is the gateway IP address. That is very important when it comes to the routing part, but we're not there just yet. So at this point, the switch has got the MAC address of user A in its MAC address table. And the switch also knows that user B is connected to whatever port on the same switch. And it can see user A is in VLAN 10, and it can also see that user B is in VLAN 10 as well. So when user A sends whatever traffic to user B and it comes into the switch here, what the switch is going to do is it's going to bridge that traffic from whatever this interface here is over to this interface here. And this is actually what's known as a MAC in the EVPN world, a MAC-VRF, or MAC Address Virtual Routing and Forwarding Table. But we'll go into more detail into a MAC-VRF in a few moments time. But just know for now that a MAC-VRF basically stores all the MAC addresses of all the connected devices within that virtual segment, in this case a virtual local area network, i.e. VLAN 10. So we are bridging user A, which is in VLAN 10, over the switching backplane to user B, which is also in VLAN 10. But what happens if there's another user connected to the same switch? And let's just say, for example, down here, draw another person. Of course, that could be a terminal, server, whatever. But let's call this MAC address C. Again, keeping it simple for user C. But let's give this a VLAN of 20, just for example. Now, at this point, bridging will not work because what we need to do is we need to go via an IRB interface. In the Cisco world, that would be called an SVI. Exactly the same thing, just different terminology. But what we need is a layer 3 routing interface, which is going to route those layer 2 frames from one virtual network over to the other virtual network, i.e. from VLAN 10 over to VLAN 20, because they're in different subnets at the end of the day. MAC address A, user A could be in 192.168.10.0/24, but MAC C, user C, could be in 192.168.20.0/24. So we need this layer 3 interface, this IRB interface, which is going to allow that inter-subnet routing. You could also call it inter-VLAN routing. It's the same thing. You're routing from one VLAN to another VLAN. You're routing from one subnet over to another subnet. But that is essentially what bridging is and what routing is. Bridging, we are bridging from one interface over to another interface. Now it may be on the same switch or it might be on different switches. Or we've got routing where we are routing between different subnets, different virtual networks. So in this would be inter-VLAN routing, but in the VXLAN world this would be inter-VXLAN routing, inter-VNI routing. However you want to think of it, to me it really doesn't matter. That routing, the IRB, is a layer 3 interface, as I've said, that allows us to route from user A all the way over to user C. So to provide that routing function, we need that layer 3 interface. But where does that layer 3 interface actually reside? This can vary in the EVPN-VXLAN world. So if I just draw here, let's call this a spine. And let's just call this device here leaf 2. and that's connected to the spine, and over here we've got another switch, another VTEP, and let's just call it leaf 1, just for example. Now that layer 3 interface, if that is located on the spine, that is what's called a centralized routing model. But if it's located on the leaves, it's called a distributed routing model. And there are pros and cons to both of these, and there's different acronyms. So this would be called as centralized routing and bridging topology or architecture, and this would actually be called an ERB or edge routing and bridging, because this is at the edge of the network itself. You might have access switches connected to this, but this is the edge of the network before you start connecting to the access switches. Or maybe there are no access switches, there's different architectures. But just know the layer 3 interface doesn't always have to be on the edge devices. It can actually be on the spines. So let's just say, for example, that layer 3 interface is on the spine here. And as we know, we've got user C with MAC address C here, and user A with MAC address A connected to the same leaf, i.e. leaf 2. Now with that layer 3 interface on the spine, what would happen is if user A wanted to communicate to user C, the leaf would have to forward that traffic up to the spine where the inter-VNI routing would take place, i.e. the inter-subnet routing, inter-VNI routing, only for it to then come back down to that same leaf device. That's called tromboning. And you want to avoid that as much as possible. However, what if the layer 3 interface was actually on the leaf itself? Well, at this point, that's a lot more beneficial because we aren't sending traffic up to the spine just for it to come back down to ourselves. No, we're actually doing the inter-VNI, the inter-subnet routing on that same device that both peers are actually connected to. However, one of the downsides of the ERB or the distributed model is that within this model, the leaf has to know about every VNI that is connected and advertised in that EVI, that Ethernet virtual EVPN virtual instance. As I said, this is more of an advanced topic, so if you don't know what I'm talking about, just check out one of these links. Please go through this information first. But with an ERB, that leaf has to know all the different virtual network instances which are in, or VXLAN network instances that are within that same EVI. But as I said, there's also this concept of MAC-VRF and IP VRF. So what is a MAC-VRF? So a MAC-VRF obviously standing for Media Access Control Virtual Routing and Forwarding Engine, and it is quite literally a table that contains the MAC addresses of all users that are within that same virtual network. So we've got MAC-VRF here, and let's just call this table 10. Again, I'm keeping it simple. And this would have MAC address A for user A and MAC address B for user B, because they are in that same virtual network. And this would then correspond to a VNI, and let's just call this 5010. That's what VXLAN is going to use to tunnel that traffic. So we've got one MAC-VRF table for the users in VLAN 10 or in VNI 5010 when we start the tunneling. But then we've got another table, and I'm going to call this table 20 for VLAN 20. And this would go to VNI Virtual Network Identifier 5020, just for example. And this would contain all the MAC address entries for all tenants which are within that same virtual network. So in this case, that would be user C with MAC address C. And that's essentially what a MAC-VRF is. However, these can then, and I'll just try and draw another table here, these can then all be within an IP VRF, Virtual Routing and Forwarding Engine table. So we could just call this table X. You can obviously give that VRF a particular table name, a particular routing instance name, but I'm just calling it table X here, just for simplicity. And within this IP VRF, we then have different IRBs. So we're going to have IRB, Integrating Routing and Bridging 10. So that would be the default gateway for all the users which are in MAC-VRF table 10. We're also going to have an IRB.20, and that is going to have an IP address for all users. It's a default gateway for all users which are in the MAC-VRF table 20. So if user A wanted to communicate again to user C, it's got to go through its MAC address VRF, which will then strip off all that layer 2 traffic in terms of the header, the MAC source MAC and the destination MAC address, and it will send it onto the IRB.10 interface, where it's then routed over to the IRB.20 interface, and then that adds on new layer 2 information. So the source MAC address will be of IRB.20, and the destination MAC address will be of user C, MAC address C. So as you can see, this is quite a big topic, but all you need to know is that a MAC-VRF is basically a switching table. That switching table contains all the MAC addresses for all the users or tenants that are in that virtual network within that VLAN. In the VXLAN world, these are then assigned to a virtual network or VXLAN network identifier. The MAC-VRFs will then have an IP VRF that will be assigned to an IP routing table. Whatever the table name is, doesn't matter. And within that, you are going to have multiple, or maybe one, there's different service bundles, but that's for a later video. You could have one or more integrated and routing bridging tables. And that allows that inter-domain, inter-subnet, that inter-VLAN routing. Because again, if user A wanted to go to user C, they are in different layer 2 networks. They need that way to get from one subnet over to another subnet. That's where the routing comes in, and that's where the IRBs allow that magic to actually happen. But let's just go through that process of stripping off that information as we go through the VTEP itself. So here we go. I've just cleaned up the display, made it look a little bit more cleaner. So we got user A, MAC address A. I've got rid of user B, wasn't serving a purpose right now. But user A is connected to the switch, and within that switch there'll be a MAC-VRF, virtual routing forwarding engine, with a table name, so I'm just calling it table 10, and all users with VLAN 10 are assigned to the VNI 5010. And again, that MAC-VRF has the MAC address entries, user A and for user B. And it's exactly the same, but VNI 5020, etc. for MAC address C, i.e. user C over here. So MAC A, user A wants to send traffic to user C. So it will send that information first to the switch. So this MAC-VRF, by the way, is inside the switch. I know it looks like it's outside the switch, but obviously I've got to draw it. So please remember these MAC-VRFs are within the switch itself. But this initial information will have the source MAC of user A, and it will have the destination MAC address of IRB 10, because that is the default gateway to get from the subnet that user A is in to the subnet or that user C is connected to. We need to get to the gateway. And then you're obviously going to have the IP address information on top of here. So the IP address will be, the source will be that of user A, and the destination will be that of user C. And it comes through the MAC-VRF, and it actually strips off that layer 2 information, and it will then forward it on to the IRB.10, because again, that is the default gateway. That's how user C is going to get out of this virtual network. And at this point, the IRB10, what it's going to do, it's going to do a lookup in its routing table of, okay, the destination IP address of MAC C is 192.168.10.2, just for example, whatever it is, doesn't matter. And it will then know that, you need to go to IRB.20. So what it will actually do at this point is it will then add on its own layer 2 information. So it's going to go from here, layer 2 will be the IRB interface .10, and the destination MAC address will be IRB.20. So we are actually, and obviously we're then going to have the IP address information here, whatever that is on the IRB interface. But we're essentially doing routing to go from IRB 10 over to IRB 20. And then IRB.20 will see, you want to get to MAC address C's IP address, and it will do a routing lookup as well. And then it will add on its source MAC address information. So that would be IRB.20. The destination MAC address will be user C. And then you're going to have the IP address information. So we're still in here going to have the source of user A and the destination of user C. And then that's forwarded down onto user C through the switching table as well. So that is very quickly the journey as we're going from one VLAN to another VLAN that is connected to the same leaf, to the same VTEP. So if there's one thing I want you to take away from this, that is, what is the function of a MAC-VRF? i.e. a MAC-VRF is a table that contains all the MAC addresses for all users, tenants, servers, etc. that are connected in that same virtual network. And the IP VRF is basically a collection of MAC-VRFs, and every MAC-VRF will have an IRB, an integrated routing and bridging interfaces associated to it. Again, if there is intra-subnet or intra-VLAN communication, that doesn't need to go through the layer 3 IRB or the IP VRF. The VTEP can just bridge that at layer 2. But as we saw, when MAC A wanted to communicate to MAC C, that is inter-domain, that's inter-subnet, that is inter-VNI, inter-virtual local area network, inter-VLAN routing. That's why we need those IRB interfaces. Obviously there's headers here which are stripped off, re-added, etc. But this is just generally the process when it's on the same leaf. Now what is the process when we've got multiple leaves and multiple devices in different VLANs or the same VLANs connected throughout the network? So for me this then brings around this question, why do we need EVPN? Why do we need Ethernet Virtual Private Network? As we've just gone through, a leaf device, leaf 2 in this example, in this video, it was more than capable of doing inter-domain routing and intra-domain bridging. I had the IRB interface configured on its own leaf, on itself basically, and that allowed it to route packets from one VLAN over to another VLAN inter-domain. It also allowed it to bridge between the same VLAN or inside the same VLAN. So why do we need EVPN? The short answer is you're not going to have all users, all tenants, all servers, etc. connected to the same leaf device, to the same access switch for obvious reasons. So users are going to be dispersed, tenants are going to be dispersed, servers are going to be dispersed throughout the network. And EVPN is, at the end of the day, a very, very good signaling protocol. I think I spelled signaling correctly. I don't know if it's 1 L or 2 L's, but it doesn't matter. It's a very good signaling protocol because it's based, or it comes from, it's a subset of multi-protocol BGP, Border Gateway Protocol. So it's very, very powerful, and it uses those update messages in the BGP world to advertise throughout that EVPN virtual instance, this EVI, who's connected to who. And so what I've done here is I've made it a little bit more interesting. So we've got user A, user B, user C, user D, and user E. And let's just say they've all got those MAC addresses, MAC address A, B, C, D, and E. Keeping it simple. And user A is connected to IRB.10. So obviously here that's going to be VLAN 10, and that's going to go to VNI 5010. And user B here, that's in VLAN 20, and that's going to go to VNI 5020. And it's going to be the same for user C. So this is going to be in VLAN 10 because it's configured to go to IRB.10. So VLAN 10, and that will go to VNI 5010. User D, MAC address D, has IRB.30. So it's a bit different. There's a reason why I'm doing that. So this will be in VLAN 30, and that'll go to VNI, just for example, 5030. And user E all the way at the end here. This is in IRB.30, or it has that layer 3 interface, IRB.30, and that is assigned, user E is assigned to VLAN 30, and let's say again that VNI is 5030. So in the EVPN world, what we're doing is we're using BGP to advertise throughout this EVI who's connected to who. So leaf 1 would advertise through spine 1 to leaf 2 and leaf 3 that user A with this MAC address is connected to leaf 1, and that would be advertised over to leaf 2 because leaf 2 has user C, which is connected to itself. It's interested in that traffic. We can see for user B that there is no other network, no other tenants out there that are interested in that traffic, that are interested in VNI 5020, keeping it simple. But we do have user D and user E, which are in VNI 5030. So for EVPN using the route type 2 is going to advertise throughout that whole EVI what MAC addresses are connected to what devices. And when that information has been learnt via EVPN, the leaves will build, because they're VXLAN tunnel endpoints, they're VTEP, they VTEP functionality. If user A wanted to communicate, wanted to send, wanted to receive traffic to say, for example, to user C, then what would happen is that traffic would go over, here's my drawing for a tunnel, I do apologize, but it would go over a tunnel, a VXLAN tunnel, and that would be VNI 5010, because they are both in the same virtual network. And I'm just going to make it a bit more interesting now. Let's also add in here another IRB, so let's call it IRB.20, and in here we've got user F connected, and that is going to go into VLAN 20, and that is associated to VNI 5020 as well. So what happens if user A wanted to send traffic to user F, or wanted to receive traffic? How would this work? Because leaf 1 has the virtual network identifier 5020 configured on its own device, and it's got that IRB interface associated to it, something happens here where we start going into the asymmetric routing model. When that traffic leaves user A, and again it's destined to user F, it will of course come up through the MAC-VRF and it will go to the IRB.10. So at this point we've done bridging, and now we're actually going to do routing, where it's going to go from IRB.10 over to IRB.20. And then it goes through the tunnel itself. Again, apologies for my drawing, but it then passes through the tunnel all the way to leaf 2, and then leaf 2 is able to then forward that packet directly via the IPF, via IRB.20 down to the user itself, user F. Very quickly, that's the asymmetric routing model. We're going to go into more detail. But what happens if user A wanted to communicate to user D or user E? At that point, this is where the asymmetric routing model fails, because we do not have VNI 5030 configured on leaf 1. It is on leaf 2, but user A is on leaf 1. And because of that, we are not able to provide that inter-domain routing, that inter-VNI routing to go from IRB.10 over to IRB.30, because there is no IRB.30 on leaf 1. We've got IRB.10 and we've got IRB.20. There's no IRB.30. And that's where the asymmetric routing model starts to fail. And that's why I said at the beginning, for asymmetric routing, you do need every VNI configured on those leaf devices if you're using a distributed model. Or if it's a centralized routing model, those spines need all of those VNIs actually configured on them. Doesn't matter either way. You have to have, for asymmetric routing, you need to have every VNI configured, in this case, on the leaf devices themselves, because from leaf 1's perspective, it doesn't know about VNI 5030. It's like, well, you want to send traffic to user D or to user E. Okay, that's great, but who are these guys? I've not received that route type 2. I don't know where that actually is in this network. And that's where the symmetric model comes into it. So there are pros and cons to both of these, and that's probably a good segue now into what is the asymmetric routing model, what are its benefits, what are its disadvantages, and then we can actually start working through what the difference is between asymmetric routing, symmetric routing, and what is that packet journey for each one of these routing models. And here we go, let's actually start talking about the asymmetrical routing model that falls within the EVPN world. And to make this example a bit clearer and a bit more hopefully informative, I'm not resorting to drawing with my Apple pen. I've actually made a PowerPoint, so there's going to be a few animations, nothing fancy, nothing exciting, but hopefully it'll be a bit more useful and a bit more clearer to you, because as I said, this is an advanced topic at the end of the day. But just so you can see what the general setup is first we've got user 1 here. Now the big thing here is I don't want you to concentrate on what the MAC addresses are and what the IP addresses are. You don't need to remember the IP addresses. For now, just know that there are 4 different users. And user 1 with MAC address A, and that IP address is in VLAN 10, and VLAN 10 is aligned to the VNI 5010. Also on leaf 1, we've also got a second user, user 2 with MAC address B with the IP address, and VLAN 20 is aligned to the VNI in the VXLAN world 5020. And all the way over on the right hand side, I'm skipping leaf 2 for a reason right now, but all the way over on leaf 3, you've got user 4 with MAC address D, just keeping it simple, and yeah, the IP address, but this is also in VLAN 20, which is aligned to VNI 5020 or 5020, however you want to pronounce it. And just to retouch on that concept that we've been discussing so far before I go any further, let's just recap on routing and bridging. So let's say, for example, here I've got my leaf device, whatever that leaf may be, and here I've got 2 egress-ingress interfaces going to different users. And let's just say here I've got a user or users in VLAN 10, and over here I've got users in VLAN 20, and just over here I've got another user here in VLAN 10 as well. Now if this user wanted, who's connected to VLAN 10 here, wanted to send traffic to whoever's in this VLAN here on connected on that access interface to VLAN 10, all the leaf 1, 2, etc. device would do, I'm just going to call it leaf 1, would do is it would bridge traffic from this interface over to that interface, and it will bridge it locally. However, because this here is a different VLAN, it is going to route that traffic to go from the IRB interface, so that would be IRB.10 over to IRB.20. Though the IRB is the gateway at the end of the day, so every MAC-VRF will have a IRB interface aligned to it for that inter-domain, inter-VLAN, inter-VNI routing. But let's say, moving back to the asymmetrical routing model, that user 1 here of MAC address A wanted to send traffic, whatever it is, to user 4 of MAC address D all the way over here on leaf 3. How does leaf 1 know about user 4's actual existence? Well, let's come back to that EVPN route type, that is the route type 2. Now all of this here is VXLAN. You're going to have VXLAN tunnels running through the spines to and from all these different leaf devices, and this will work with the assistance of the signaling protocol EVPN. So VXLAN and EVPN is between those leaf devices and those spines. It's not from the leafs down to the users themselves. That would be your traditional Ethernet broadcast flood and learn type of approaching. But with EVPN, what we're doing for leaf 1 to learn about user 4's MAC address is leaf 3 would advertise through one of the spines over BGP that root type 2 message, which contains the MAC address D, or obviously that is user 4 as I've wrote down. And at that point here, leaf 1 actually believes and can actually see as such from its perspective, hang on, I've got user 4 with MAC address D connected to me. It sees it locally. And within that MAC address D, this is also assigned to VNI 5020 with VLAN 20 as well. And my writing is getting worse and worse as I keep doing these videos. But it sees and learns that user has been locally connected. But obviously in reality, it's not. User 4 is connected to leaf 3 and user 1 is connected to leaf 1. But what we do have is we've got this MAC-VRF. As we know, that is just storing the MAC addresses for all those tenant servers that are within that virtual domain, that subnet, whatever it may be, just containing the MAC addresses. And then we've got this IRB interface, so IRB.10 for VLAN 10 and IRB.20 for VLAN 20. So as the user 1's traffic comes up through the MAC-VRF or into the MAC-VRF, what's going to happen at this point is that leaf 1, that MAC-VRF is going to bridge that traffic onto the IRB interface. So it's going to bridge it over to IRB.10. And at this point here, it's then going to do a route lookup. It's actually going to revert to its routing table to see, you want to get to this IP address over here, or that IP address in itself. Where does that actually belong? And at which point it's going to see, hang on, to get there, I need to go through IRB.20. So what does it do at this point? The second part after it's bridged is it's then going to route from IRB.10 over to IRB.20. So first we bridge and then we're actually going to route itself. So we've done our bridging, and just to make it a bit clearer, we've done our bridging up to the IP VRF with IRB.10, and then we route over to IRB.20 because user 4 sits within the same VNI that is locally configured on leaf 1 itself. And at this point, it's actually very straightforward. Whether it goes through spine 1 or spine 2, it doesn't matter. Leaf 1, in using the IRB.20 interface, it's going to see, to get to leaf 3, I need to go through this particular tunnel, and that is going to have the VNI of 5020. And then that traffic comes in. So if I just follow the path, it comes up to the MAC-VRF, bridged over to the gateway, IRB.10, routed over to IRB.20, where a route lookup takes place, and sees, leaf 1 sees I need to go via this VTEP tunnel to get to leaf 3. And then that traffic is passed through the tunnel itself with VNI 5020, where it then gets to leaf 3 itself. So the traffic has now arrived at leaf 3. Now, what do you think happens at this point? So will the leaf 3 do any bridging, or will it do some routing? Just have a think about that just for a second, and I want to steer you on the right path. We have routed over from VNI 5010 with the IRB.10 interface over to VNI 5020 with the IRB.interface IRB.20. So first we bridged, then we routed, and then it's come over the network to leaf 3. User 4 is in VNI 5020. We have already routed from VNI 5010 over to VNI 5020. So the answer is no, we do not need to do any routing on leaf 3. At this point, it is only bridging that we do, because that received traffic is already in the same VNI that the destination is in. Leaf 1, the ingress VTEP, done the bridging through the MAC-VRF up to the default gateway, IRB.10. It then routed over from 5010 to VNI 5020. and then the IRB.20 interface routed that traffic through the VTEP tunnel with VNI 5020 to leaf 3. It's already in the same VNI when it's received, and then all leaf 3 needs to do is look in its MAC-VRF table to see where does MAC-D actually reside. What is the egress interface? The received traffic is already in the same virtual network. It's already in the same VNI, so no routing needs to take place on the egress leaf when it comes to asymmetrical routing. So let's just have a quick summary into the asymmetrical routing. So first, what we're going to do is we're going to bridge, and we're going to bridge through the MAC-VRF for VLAN 10, which is aligned to VNI 5010. And this is just going to go to its default gateway, which is IRB.10. Now, at this point on the IRB.10 interface at the IP VRF level, we then have to route over to IRB.20 because IRB.20 is aligned, is configured to be the loopback 0 interface, the IRB interface for VNI 5020. So first we've done bridging, then we're doing routing. And when we get to that egress leaf, that is leaf 3, all we're going to do at this point is bridge that de-encapsulated traffic through the MAC-VRF onto the destination, i.e. onto user 4. A lot of people think this point here is routing. You don't need to route traffic that's already in the correct virtual network. You don't need to route traffic that has been received on the same VNI that that VLAN is aligned to. So only bridging needs to take place when that received and de-encapsulated traffic is in the same, or was in the same VNI that that destination actually resides in. At that point, it's just bridging, it's just switching. But let's now look at it from a packet journey. So we've got the source here, which is user 1. And again, you can see all the information down here. And the destination is user 4 with all the information down here on the PowerPoint. And we've got these intermediary steps. We need to go from the source over to leaf 1. Leaf 1 needs to then forward it over to, just for in this particular example, spine 1. Could be spine 2, but I chose spine 1. Doesn't matter. And then spine 1 is going to switch, because all the spines here are doing is switching, and it's not really, it's a lean spine at the end of the day. It's just forwarding traffic. And spine 1 will then switch onto leaf 3, where this VTEP here will de-encapsulate all of that VXLAN overhead, come out with the original, almost, Ethernet frame and packet, and forward it onto the actual destination itself. So first let's look at that overhead that user 1 sends to its default gateway, that is the IRB.10 interface on leaf 1. So user 1 here will send traffic up to leaf 1, and it passes through its MAC-VRF, the switching table for that virtual routing and forwarding table, just contains all the MAC entries. And of course we've got a payload here. That payload will be that ICM ping. It will be that application which is running. It really doesn't matter in this example, in this context, there's going to be a payload. But what is the destination? Well, user 1 wants to get over to user 4, and that will have the destination IP address here of 10.10.20.2, and so that would be the destination IP address here. I've only put user 4 to keep things simple. I think if there's lots of numbers in these headers, A, it's not all going to fit in, and B, maybe a bit too much information. That's why I've wrote the information down here, and you can refer to it if you should wish. Who's going to have the source IP? Well, of course, it's going to be user 1 with this IP address here, 10.10.10.10, I think, 10.10.10.1. So that's straightforward at this point. Now, this frame, this IP packet is coming up to its default gateway via the MAC-VRF up to the IP VRF where there's IRB.10. And so the destination MAC address is going to be that of leaf 1 at this point, because we want to get out of the network. So the destination MAC address is that of the interface, the virtual interface that's going to allow me to get out of the network. So that is leaf 1, IRB.10 on leaf 1. And the source MAC is user 1. It's where the frame is coming from. But when that frame is passed into the leaf 1's IP VRF, what it does is it actually strips off this overhead here. Now, the payload is always going to remain there, unchanged. The destination IP address is going to remain of user 4. The source address is going to, in terms of the source IP, is going to remain that of user 1. But we're going to have two new pieces of overhead here. And as you can see, the destination MAC address is now that of user 4, because that is the end destination at the end of the day. And the source MAC is that of leaf 1. Why is it that we no longer have the destination MAC address of leaf 1 here and the source MAC address of user 1? Well, do recall that I said that all of this here between the leaves and spines, this is VXLAN. This is where we've got the VXLAN tunnels and EVPN signaling running on top of the BGP overlay. And VXLAN requires an outer header, an outer IP address, destination MAC address, and a VNI and a source MAC address, etc. But it requires an outer IP address, outer MAC addressing, and an outer VNI header, the shim header. And so all of this is actually what's called the inner header. So all of this is actually inside the VXLAN overhead. You'll see what that will be in just a second. And because this is now inside the VXLAN world, i.e. we're going to start routing over the VXLAN network, we need to have that source MAC address of leaf 1 within the inner packet, the inner part of this VXLAN overhead. And the destination MAC address is that of user 4. Again, this is all within VXLAN. We've learned destination 4, user 4's MAC address via EVPN. And because we're now going to be routing through those VXLAN tunnels, VXLAN requires an outer IP and MAC addressing and UDP, of course, and a VNI shim header. But it also requires that inner header to reflect that of the tunneling capability. So think of where's this tunnel coming from? So it's from leaf 1. And where's it actually going to? What's the final destination? And now we've got all the outer header here. So this is actually the outer header you will get with the asymmetrical routing model in the EVPN world. So now we've got VNI 5020 because the destination user 4 with MAC address D is in VNI 5020. Don't forget we routed from VNI 5010 where user 1 actually resides. We routed it over on leaf 1 from the IRB.10 over to the IRB.20 where it done its route lookup and then forwarded that traffic through the VTEP tunnel from IRB.20. So we got the destination VNI 5020. Now the destination IP address, the VTEP tunnel is coming as such through the network like this from one VTEP over to the other VTEP. And of course, this is going to have a source. This is going to have a destination. And it's not all displayed here. The PowerPoint will get way too interesting. But the destination IP address will be saying, well, this VXLAN tunnel needs to go to leaf 3. And leaf 3, it's loopback 0. It's using loopback 0 at the IP addressing interface will be that on leaf 3. The source IP is coming from leaf 1. It's where the VTEP tunnel has originated from. And because this is going through spine 1, we need to say at layer 2, the next hop is the destination MAC address, hop by hop. At this point, the next hop is spine 1. So this frame, as I said, is going to go up to spine 1. And that frame is coming from leaf 1. And at this point, spine 1 has now got all of this information here, but does it actually need to look at all that information? The answer is no, it actually does not. The next step in the process, you can see that that inner VXLAN header has not changed a single bit. And the outer VXLAN header, we still have that shim header with a VNI of 5020. The destination IP address is still that of leaf 3. The source IP is still that of leaf 1. That's where the tunnel terminates, it's its destination, and it's where it's come from, it's where it's sourced, respectively. But now because spine 1 is forwarding this traffic down to this VTEP tunnel, leaf 3, we're now going to have a destination MAC address of leaf 3. There was a little bit of a typo there. I did correct it. You might have noticed it did say leaf 1. That's incorrect. But the destination MAC address for this next hop is going to be leaf 3 at layer 2. And this is coming now from spine 1. So at this point, the inner header remains the same. All these header information here remains the same. It's only these two parts here which have changed because the outer MAC addressing needs to change hop by hop as we go from leaf to spine, leaf 1 to spine 1, and then from spine 1 down to leaf 3. And now leaf 3 has received that tunneled traffic. And what's it going to do at this point? It is going to remove all of that outer information, all of that outer MAC addressing and the outer IP addressing and even that VNI 5020. It's not needed at this point because this VTEP is doing decapsulation of that information. So all of this is gone. It's no longer needed. But that VNI 5020 here is really important because it allows leaf 3 to identify, this tunnel traffic has come through a tunnel which is aligned to VNI 5020. VLAN 20 is configured to be part or with aligned to VNI 5020. And you want to go to this destination MAC address here. And at this point, all leaf 3 needs to do is see, you've got destination here of a destination MAC address of user 4. This came from leaf 1 because that's where this tunnel traffic has originated from. And this is the destination IP address user 4. So all it's going to do is a route lookup here to see, well, what is the egress interface that this traffic needs to go out of, and then forward it down to the destination from there. And then guess what? We're at the end. That is asymmetrical routing. But if I was to summarize, so just in quick summary, first the ingress leaf. If we look at it from the ingress leaf perspective, so that will be leaf 1. First, when it receives users 1's traffic, it's going to bridge via the MAC-VRF that the user 1 is located in up to that gateway. The gateway is the IRB.10 interface. Now here, ingress leaf 1 will do a route lookup. And in this route lookup, it will see, you need to get to user 4. And I now need to route this traffic over to VNI 5020 and through IRB.20 interface. So first we're doing bridging and then we're doing routing on the same ingress leaf. But what about the egress leaf? At the egress leaf, the VTEP will de-encapsulate that received tunneled traffic and it will remove all of that header within that de-encapsulation. But here it's only going to bridge that traffic onto the destination, which is user 4, through by looking up the MAC address in the MAC-VRF table. And the reason why it's not doing routing is because before the de-encapsulation, it would have seen the VNI of 5020, and the routing over here is where we route over to 5020 as well. And so these are exactly the same. And as such, no routing needs to take place on the egress leaf. But what are the limitations? What are the problems? What are the challenges when it comes to this asymmetrical routing model? And there's two that I actually know of. First one, let's actually look at it from source to destination here. We've got the destination is in VNI 5020 and the source is in VNI 5010. And bridging and routing aside, what we saw is that tunneled traffic went through spine 1 over to leaf 3, and that had the VNI of 5020. And that's fine, but what if the user 4 wanted to send traffic back to user 1? So now user 4 becomes the source and user 1 becomes the destination. Well, at this point, we could have a separate tunnel going across the network where we actually go through spine 2, and that would go through the tunnel of the VNI tunnel of 5010 because the destination is in 5010, and leaf 3 will route it after it's done the bridging through the MAC-VRF. It will then route it from IRB.20 over to IRB.10 before actually forwarding that traffic onto the destination user 1. So you could get, and you will get in the asymmetrical routing model in EVPN, a asymmetrical routing, as the name implies. You're going to get packets, encapsulated packets being sent in different directions throughout the network. And maybe spine 2 is being hit by more congestion, maybe it has less capacity than that of spine 1, so on and so forth, and it could impact the underlying traffic that's going through that tunnel. Whatever it may be, that's one of the limitations when it comes to asymmetrical routing. But I said that I know of 2. The second one is when it comes to what it assumes in terms of the local VNIs. And notice, and you've probably noticed, I've not mentioned user 3 at all so far. And that's because user 3 with MAC address C is in VNI 5030, and that is aligned to VLAN 30. Now, with the asymmetrical routing model, all of the remote ends, in terms of remote destinations, which are advertised and learned via that route type 2, route type 2 advertises all of those MAC addresses. So that MAC address is going to be, of user 3, is going to be advertised from leaf 2 over to leaf 1, and of course over to leaf 3 as well. But remember what I said, that with the asymmetrical routing model, leaf 1 or any leaf requires all VNIs to be configured locally because it's doing that bridging first and then the routing over from one VNI to another VNI. Does leaf 1 have a VNI configured locally of 5030? Does it have any users in its MAC-VRF for VNI 5030 with obviously the IRB.30 interface? Does it have any users within that VLAN 30 as well on leaf 1? The short answer is no. So if user 1 wanted to send traffic to user 3 and it comes up and it says, yeah, the destination IP address is 10.10.30.1, at this point leaf 1 is going to say, well, I know where that is because I've learned that via the route type 2, but I do not have this VNI configured on me, and as such I cannot route over from VNI 5010 over to VNI 5030 because that's not configured locally. So with asymmetrical routing, you need to have every VNI that's configured throughout that EVI, that EVPN virtual instance, needs to be configured locally on each of these leaf devices. So even leaf 3 would need VNI 5030 as well, and 5040, 50, all the numbers. And there's obviously a lot of numbers that you can get within that 24-bit VNI. So those are the 2 limitations of asymmetrical routing, and that's why we have symmetrical routing. I'm not going to say symmetrical routing is perfect, but it addresses these challenges when it comes to asymmetrical routing. So let's now go through this concept of symmetrical routing. Really, a lot of the heavy lifting has already been done because we've already gone through what is a MAC-VRF, what is an IP VRF, what is an IRB interface or SVI in the Cisco world, etc. And asymmetrical routing. Symmetrical routing is not that much more different, to be honest. The only big difference is we have something called a transit VNI, a transit VXLAN or virtual network identifier. We'll come on to that. But in this scenario, in this example, we'll stay with user 1. So user 1 is the source, but now our destination is user 3. User 3 is in VNI 5030. User 1 is in VNI 5010. As we just discussed, there is no VNI 5030 attached, connected, configured locally on leaf 1. It simply does not exist. So in the asymmetrical world, we could not have leaf 1 routing through the VTEP tunnels all of user 1's traffic to go to user 3 on leaf 2, because leaf 1 doesn't know about VNI 5030, doesn't have that VRF, and thus it can't do the routing, even if it did learn about the MAC address C that user 3 actually has via EVPN. And this is where symmetrical routing solves those problems. What we actually have in the symmetrical routing is this transit VNI, which is basically a different VRF, a virtual routing and forwarding instance, to go from the source VTEP leaf 1 to the destination VTEP leaf 2. So we would actually have our tunnel here, and again we'll use spine 1, and we got the tunnel here, and this would be a transit tunnel, and it might be something like 10,000, just for example. Pick any number, doesn't matter. But it allows us to then transit through the tunnel the traffic from the source leaf 1 through the network to leaf 2, where it gets to that destination itself. And thus we don't need every VNI configured on every single edge device, every single leaf in the network. So we're using the transit VLANs to get away, to get through, to get past those challenges that asymmetrical routing actually brings to it. And before we go through the packet journey, let's first take it through the bridging and routing with the symmetrical routing model in EVPN. So we've got our source here. So this source doesn't matter at this point, and we've got the destination. Actually, let's say the source is still user 1 and the destination is still user 3 with MAC address C. So as we know, that information comes up to leaf 1, it goes through the MAC-VRF, the switching table, which basically contains all the MAC entries for that particular VLAN. That VLAN is associated and configured to a particular VNI 5010. Appreciate it's a bit small there, I was running out of room. But as we know, we are then bridging up to the IP VRF locally, and we're using the IRB 10 interface, which is associated and configured to be part of VNI 5010. We are then routing, as we did with the asymmetrical model, we are routing to go from IRB 10 for VRF 5010, VNI 5010, over to VNI 100, I'm calling it here. So we have then routed over to that transit tunnel. So let's just write here that transit tunnel is VNI 100. So now we have, first we've bridged up to the default gateway. We have then routed over to the transit network, which has that VNI of 100. And then we are routing across that VXLAN network through the tunnel to that destination leaf. And of course, we've got an IP VRF here, and we've got VNI 100 configured on the egress leaf with IRB 100 as well. And now at the egress device, what we are going to do is we need to route that traffic from the received transit VNI over to the destination VRF. So step 3 is actually we're going to route from the back from the transit VRF to the destination VRF, i.e. we're going to go from VNI 100 to the destination VNI, which is 5030. And then once that leaf device has, of course, de-encapsulated, etc., all that traffic, we are then going to bridge locally that traffic through that MAC-VRF. Again, look up the destination MAC address and see what is the egress interface. So really, with symmetrical traffic, we have first a bridge. We're going to bridge it up to the default gateway, which is the IRB interface. 2, we are then going to route that traffic from the source VNI to the transit VNI. We need a transit VNI, a transit VRF, transit VRF in symmetrical routing. So we're going to route it from the VNI 5010 to whatever that transit VNI actually is. And when it gets to that destination leaf, we are then going to route it back from that transit VRF, that transit VNI, to that destination VNI. In this case, that is 5030. And finally, once it's inside that domain, once that traffic is inside the correct virtual network, we can then refer to the MAC-VRF table and bridge it locally, and out the egress interface it goes. So these two happen at the ingress leaf, and these two happen at the egress leaf. So there are more steps involved, but really the key point here is that you need this transit VNI to go from ingress leaf to egress leaf, and we are going to, yes, bridge packets up to that default gateway on the ingress leaf. We're then going to route it over from one VRF to another VRF, from one VNI to another VNI. Through the transit VXLAN tunnel it goes with whatever that VNI actually is. And when it's received to that egress leaf, we're going to route it from that transit VNI to the destination VNI and bridge it locally. So in terms of the packet journey, we still have this source of user 1, which is in VNI 5010, or I'll just write here VNI 5010. And the destination is now user 3, which is in VNI 5030. And again, you can see more of the addressing, if you want to call it that, more of the details on the PowerPoint on the display. But really, in terms of that initial inner header, Ethernet frame, IP packet, everything's the same. We've still got our payload, but now the destination IP address is, of course, that of layer 3. The source IP is that of user 1. The destination MAC address is that gateway. It's the IRB interface, IRB.10 on leaf 1. And the source MAC address, of course, all of this information is coming from leaf 1. So that is the source MAC address. What does it look like when we get to leaf 1, i.e. when it's passed up to the IRB interface and we start to see how it's going to route through that transit traffic? And just like in the symmetrical model, we still have the payload. We still have the destination IP address of user 3, and we still have the source IP address in terms of the inner packet, the inner headers of that VXLAN traffic. That's the same. It doesn't change throughout any of these steps, and it's the same in the asymmetrical model. But I've highlighted in green what is different here. So the destination MAC address is now of leaf 2, whereas recall that in the asymmetrical model, the actual destination MAC address was that of user 4. The reason why we're now defining the destination MAC address of user of leaf 2, is because leaf 1 doesn't actually know about the destination MAC address of user 3, i.e. MAC address C here. However, VXLAN still requires this inner header to actually be filled, to actually be completed. And as we know, in the asymmetrical model, we were using via EVPN, that route type 2, to advertise all of that MAC addressing. But in the asymmetrical model, the route type 2 is not advertising the address of user 3, i.e. MAC address C. Now what it's actually doing is the route type 2 here is actually advertising the address, the MAC address of leaf 2. So within the route type 2, you have your extended community. So I'm just going to do com here as part of the payload. And within here, you've got something called the system MAC address. And the system MAC address is basically the MAC address of the leaf, i.e. leaf 2. And so that is advertised over to leaf 1. And because of that, leaf 1 can say, using the symmetrical model, well, the destination MAC address is not that of actually the end host, i.e. user 3, but the destination MAC address for this transit traffic, because don't forget, all it is a tunnel going from one VTEP to another VTEP. It's not to the end destination, but the destination MAC address is now leaf 2, whereas the source MAC address is still leaf 1, of course. And here is the outer VXLAN header. So I'm just going to write outer at the top here. So the other difference, again highlighted in green here, is the VNI. So now this virtual network identifier for that VRF, for that virtual routing and forwarding, for that VRF table, is that transit traffic. So now this transit traffic going from the source leaf to the destination leaf, leaf 2, will have a VNI of 10,000. And the destination IP address is that of leaf 2. So that will be the loopback 0 interface that we're using to build those tunnels to and from those different VTEPs, those different leaves. The source will be leaf 1. And now, this is all obviously layer 3. Here is layer 2, and that is hop by hop. So the source MAC is from leaf 1, but the next hop in terms of the end-to-end path is onto spine 1. So hence we got spine 1 here. And at this part, when it comes to spine 1, then forwarding the traffic down to leaf 2, nothing's changed. You can see the inner headers of the VXLAN overhead remains the same. The payload's not changed, the IP addressing's not changed, the MAC addressing's not changed. Only when it comes to the outer traffic, there's only one thing that's changed, and that is the MAC addressing. So now the source MAC now lists spine 1 because it's originating now from spine 1, and the next hop is leaf 2. So when leaf 2 receives this traffic, it's going to see, this destination MAC address is that of leaf 3. I am leaf 2, sorry, I am that of leaf 2. And also the destination IP address is that of leaf 2. So I know this received VXLAN traffic is for me, and as such I can de-encapsulate, I strip off all of this overhead. But I'm also going to look at this VNI, this virtual network identifier of 10,000, and I'm going to check within my IP VRF routing table what IP VRF that this destination IP address actually belongs to, and at which point it's going to know that it belongs to the VNI or IP VRF that's associated to that VNI 5030. And at which point, once it's referred to and discovered that this destination IP address is in IP VRF table 5030 and associated to VLAN 30 as well, is then going to refer to that MAC address VRF, that MAC VRF, to see what is the MAC address that's associated to this IP address and populate that information in here. And then it's also going to say the source IP address is still that of user 1, it's not going to change that, but the source MAC address is that, of course, of leaf 2, and then it just forwards, bridges that traffic down to user 2. So really there's 2 or 3 subtle differences there between asymmetrical routing and symmetrical routing. First is, and let me just tidy up the display. There we go, that's a bit different. So first, when it comes to symmetrical routing, that inner part of the destination MAC address is of that end leaf device, is of that end VTEP. It's not of the end destination when it came to asymmetrical routing. So symmetrical routing, we've defined the inner destination MAC address is that of the end VTEP, leaf 2 in this case, whereas with asymmetrical routing, the inner destination MAC address was actually of the end user themselves. And then we've got this, actually it's down here, we've then got this transit VNI. With asymmetrical routing, this was, as we saw, 5020 because that was where user 4 actually resided in. But now we've got this transit traffic where we had this transit VNI of 10,000, I think it was, to allow both of these leaf devices, leaf 1 and leaf 2, to use the same VNI to send encapsulated traffic through the tunnel to and from the same source and destination. And finally, at the end here, we've done our lookup where we took that VNI, looked in our IP VRF routing table, we checked out the destination IP address of user 3. In here, we could see what MAC-VRF that IP address was configured to, and thus through here, we can then discover what the MAC address was of user 3 and send that on to user 3 as well. And I've just noticed that there's another mistake here. That should be 3, not 2 there. So there we go, everybody. That is the end of this chapter. That is the end of this part in this EVPN-VXLAN series. We've gone through a lot of information. As I said, this is an advanced topic, and it is an advanced topic of the EVPN routing protocol. There's two different types of routing methods, asymmetrical and symmetrical. But before we even went there, we went through firstly, initially, what is a MAC-VRF or virtual routing and forwarding table? What is the IP VRF, virtual routing and forwarding engine table, whatever you want to call it? And as we learned, a MAC-VRF is essentially storing all the MAC address entries in its table for all tenants, servers, etc. that are connected to that virtual network. And that MAC-VRF will then, to allow inter-subnet, inter-domain, inter-VNI, inter-VLAN routing, it will then forward or bridge, hence IRB, integrated routing and bridging, it will bridge that traffic which is destined to a different network up to its default gateway, which is the IRB interface. And at that point, the IP VRF will do a routing lookup in its routing table to see, well, where is that destination? Is it locally configured? And do I need to go through a transit VNI, or can I do asymmetrical routing? And that then brought on the topic of what is asymmetrical routing and what is symmetrical routing. And with the asymmetrical routing model, we discovered that you need every VNI configured on those leaf devices to allow that asymmetrical routing to take place. Without that, it simply will not work. And that's where symmetrical routing came into it. Symmetrical routing is more complex, there's more to configure, but it addresses the limitations, the problems asymmetrical routing brings to the table. So as always, I hope you found that video, this content, useful. As I said, it was an advanced topic. EVPN is a huge protocol, and to be honest, we've not even scratched the surface. That's how big it actually is. But I hope you found this content useful and informative. If you liked this, please give me a thumbs up. It's the best way to support my channel. Any questions or comments, let me know down in the comments box. I really do love hearing from you all. Other than that, thanks for watching and goodbye.